So welcome to Saugatu Basu from Basu, and he will be speaking about complexity theory of constructible sheaves.
Okay, is it point to? Okay, okay, so yeah, so maybe if I have to give a talk like this, I should justify a little bit. So I'll start with some motivation, and then I decided to break it up into three parts. The first part would be mostly what I would call qualitative, and some of it, most of it will be familiar to many people. Second part would be quantitative aspects of these qualitative things, and the third part would be, if I get to it, to be more complexity theoretic. I'll explain all this. So motivation. So why talk about constructible shifts? It will be, I hope, more clear when we go down the talk, but you'll see that it provides a more natural geometric language than more expressiveness than just the first order logic of Starsky style. And it also provides what I think of in my mind as a topological generalization of quantifier elimination, Symbolic-Numeric theorem. And it's interesting to study quantitative algorithmic questions in this more general setting. And of course, they appear in other areas of mathematics, in the theory of D-modules, even in applied areas like computational geometry. And so there are some interesting extensions of complexity classes in the sense of Bloom, Shub, and Smale, which are very much related to, over the real numbers, this is very much related to semi-algebraic sets, and then these some generalizations of these P versus NP type questions, which in fact would be easier to resolve than the classical ones. And finally, quantitative study of sheaf cohomology is already a very interesting topic on its own because of its applications in algebraic geometry. Okay, now background, and please stop me with questions. So, semi-algebraic sets, subsets of Rn. You can take R to be more generally a real closed field, but for this talk we can just restrict to the real reals, defined by Boolean formulas. The atoms are of the form P equals 0 or P positive or P polynomials. The semi-algebraic map is a map whose graph is a semi-algebraic set. Now, so it kind of follows directly from these definitions that that semi-algebraic sets are stable under all kinds of finite set operations and taking products, more generally fiber products over polynomial maps, and also taking inverse images under polynomial maps. Right? So the fact that they are stable under these operations is just a consequence of the definition. But what is less obvious, but through this harder fact, Tarski-Heisenberg theorem, is that not just that they are stable under taking fullbacks under polynomial maps, but they are also stable under taking direct images of semi-algebraic sets and polynomial maps. Or in terms of logic, the first order theory of reals admit quantifier elimination. Okay. Now, this might sound a little pedantic, but I just want to reformulate what I just said in terms of arrows. So, if F is any map between two sets, then of course there are these induced maps between the power sets of X, power set of Y, where the middle one is just taking the inverse image, and the two ones that go in this direction corresponds to the existential and the universal quantifiers. Well, that's the definition of these things. And these pairs are not quite inverses of each other, of course, but there is a kind of adjointness relation which is also quite obvious. That if you think of these power sets as some category whose arrows are just inclusions, then the existential one is left adjoint to the pullback, which is left adjoint to the universal. And this is just a fancy way of saying that for a subset A of X and a subset B of Y, if f exists A is a subset of B, it means A is a subset of pullback of B, and if A and the other one. Okay, but this is just valid for all sets. And so, if you denote by S of X for any semi-algebraic set X, the set of all semi-algebraic subsets of X, and if you have a semi-algebraic map, or let's say a polynomial map, then the Takacs-Seidenberg can be restated as saying that these F exists, F all, and F star, they carry semi-algebraic sets to semi-algebraic sets. So the functors from this category to that category. And that there is the adjointness in the sense that the top one is left adjoint to the middle, which is left adjoint to the bottom. Okay, but there's nothing really, just saying Takacs-Seidenberg in terms of arrows. But in fact, I said that there are these laws, so the fact that semi-algebraic sets are stable under taking pullbacks is obvious. Proving that they are closed under direct images is less obvious, still true. But in fact, there is yet another slightly harder fact that more than just Takacs-Seidenberg is true. That in fact, semi-algebraic maps can be trivialized in the following sense. That we say that a semi-algebraic map is trivial, semi-algebraically trivial, if there exists a trivialization phi, which is fiber preserving homeomorphism from X to the product of a particular special fiber times the base. The fact that that triangle commutes is just saying that this homeomorphism phi takes fibers to fibers. Well, not all semi-algebraic maps are trivial, but the theorem due to Hart says that if you have a map, then there is a finite partition of the base into locally closed semi-algebraic sets, such that restricted over each element of the partition, the map is trivial. So here's a stupid picture of this. If your map is a projection from the green to, well, it's two colors, I don't know why, but to the base, then a semi-algebraic partition of the base would be the singular point and the complement of it. And over each one of them is. So this is, I'll say, a generalization of Takacs-Seidenberg because it remembers not just where the fiber is non-empty, but it remembers, in fact, the homeomorphism type of the fiber. So, for example, it's a proof that there are, a consequence of this theorem is that there are only finitely many semi-algebraic homeomorphism types amongst the fibers of a fixed semi-algebraic map. So, but it has some drawbacks from the point of view mostly of complexity. Well, homeomorphism type is something that's kind of difficult to quantify. It's undecidable to check, but this is not going to be so important for us. but also that the best complexity upper bound known for this induced partition of the base, if you have a fixed semi-algebraic map, is doubly exponential. And whenever I say things like doubly exponential or singly exponential or polynomial, I mean it is doubly exponential, singly exponential in the number of variables. So if you have a semi-algebraic map from Rn to Rn, then this induced partition, the best that we know, can be defined by polynomials whose number and degrees can only be bounded doubly exponentially in the number of variables. Okay, but there is reason to believe that might be this bound should be singly exponential, but we do not know how to prove this. So the formalism of constructible sheaves seems to be a compromise, and we'll see in a moment, because in sheaf theoretically we only remember amongst these fibers some kind of a homological equivalence. Not so fibers are allowed to be so we don't want that partition where the fibers are all homeomorphic, but a weaker equivalence relation, which would imply, for example, that all the over a fixed element of the partition, the fibers have isomorphic homology groups. So I'll define to some extent what constructible sheaves are, but that's one of the motivations for it. So a little detour into, of course this will be very quick and might be not so useful, because if you already know some sheaf theory, this is not going to be useful, but if you don't, I'm not sure whether it will help, but still I'll try. So we'll fix our, so in general for over any commutative ring, but let's for simplicity take A to be just a field of rational numbers. So whenever I write A, it should be Q. So a pre-sheaf over a topological space, well, it associates to every open an A module or a vector space over Q for us now. And whenever you have an open inside and an open V inside an open U, there is a restriction homomorphism that restricts from f of U to f of V. And it has to satisfy the axioms that you expect it to satisfy. So the restriction from U to U should be the identity, and it should have the obvious transitivity restriction. Okay. And so we call pre-sheaf to be a sheaf if in addition it satisfies these two other axioms, that if you have a section S, which is an element of f of U, that if you have two sections that agree on an open cover, then they must be equal. Or in other words, if S restricted to each UI in an open cover of U is 0, then it should be the 0 section. And this kind of local to global axioms, which says that if you have sections over each UI which are compatible over the intersections, then you can construct a global section over U. So this is of course very standard definition of sheaves that you see starting from complex analysis. But and also the stock of a sheaf at a point, which would be of interest to us, is the inductive limit of the f of u's over all neighborhoods U containing X. But constructible sheaves, unfortunately, so first of all, we are talking about sheaves of A modules where A is a fixed ring. So we are not talking about sheaves of OX modules, like it's more common in algebraic geometry. So the coefficients are coming from a fixed ring. But in order to make a nice statement, which would be generalization of Tarski-Seidenberg, one needs to enlarge this category from sheaves. We have to go to the derived category. So So of course, the derived category is defining properly is several pages, but what you should think of it, the objects are not just sheaves but complexes of sheaves. But these complexes of sheaves are quotiented by a very complicated equivalence relation. So first of all, you consider morphisms are homotopy classes of morphisms of complexes, and then you quotient out by a certain class of arrows to get to the actual category. Yes?
Is it possible to give a quick definition of complex sheaves? No is an okay answer. What is a complex?
A complex, a complex of vector spaces is just a sequence of vector spaces with homomorphisms such that the composition is of any two is 0.
Infinite in both directions, or?
For the moment it's infinite in both directions, but you see that
Okay.
B over there, so we'll soon make it bounded. So,
Bounded in both directions?
yeah, bounded in both directions.
Uh-huh.
And then the complex of sheaves is, but when you do this equivalent, you take this quotient to get to the derived category, you do not, so this is more of a warning, it is not going to come up too much in what I discussed, that it's no longer an abelian category, exact sequences that will be replaced by something called distinguished triangles. So there is no notion of kernel. But for our purposes, it's okay, of course, to think of an object as a complex of sheaves, forgetting about this complicated equivalence. And if X is a point, and your ring is just Q, then in fact it's perfectly okay because an object, a complex, is isomorphic in the derived category to the homology complex. So it's you just take the homology and take the differentials to be all 0. It's not true if X is not a point, but if you're in the category of just vector spaces, the object in the derived category is the same. So in other words, a complex is this. So this is just a way of saying that you have yes.
Just to make sure, the differentials here are these restrictions to boundaries, co-boundaries business?
No, so this is an abstract complex, right? So it doesn't need to come from.
Okay, but they're the maps within the is there a complex?
Maybe yeah, so for me, at the moment, it's just, you see, I put over there. So it's just so you have differentials.
Do you mean one of the subscripts to be upper and one lower?
Oh.
And
Both
it
are
has to
up.
go down then, right?
Well, upper will go up.
Oh, yeah, upper goes up, yeah, right. Okay, yeah.
Okay, great, thank
And
you.
so it's just
Okay,
that.
great. Thank you.
So that's just the complex.
Okay.
And I'm saying that, of course, this represents some object in the derived category, and as long as your field is Q, then this is isomorphic to, so you can take the homology of this complex, and you can take the complex which is HI of C dot, and put a 0. So these two complexes are isomorphic in the derived category, but only for complexes of vector spaces. If you have sheaves, then it's
Well, no, you mean only for a point.
only for a point.
It doesn't have to be a vector space, right? It's for any A module.
That also I'm not sure whether it depends on the ring, but certainly for a point and a vector spaces. So there is a famous theorem of Deligne on something called a decomposability theorem that says if nice non-singular projective variety, something like this is true, but certainly not in general. Okay, so now we can say something. So So just like over semi-algebraic sets, we have these pullbacks, images, doing set theoretic operations. So if you have a sheaf on X and a sheaf on Y, so there are certain corresponding sheaf theoretic operations. So this is the notion of a pullback of a sheaf. So if you have a sheaf G on Y, then you can pull it back, and the definition of pullback is one that you it's easy. And in fact, this is a so in fact, as a kind of point of comparison with Tarski-Seidenberg, we saw that the fact that the pullback of a semi-algebraic set under a polynomial map is semi-algebraic is an obvious fact, while the fact that the image of a semi-algebraic set under a polynomial map is semi-algebraic requires effort to prove. So taking inverse images is simple, pushing forward complicated. And we will see that this persists for sheaves. So for example, F inverse is example of an exact functor. I don't want to define this, but it's a simpler operation than taking the, so you can do the other, you can consider the other operation that if you have a sheaf on F, Ln X, you can want to push forward the sheaf to Y. And here you would want to go to the derived category, because the push forward, the direct image is not an exact functor. So it's left exact, not right exact. So you should take the higher direct images. So there exist higher direct images, but proper way of doing it is to go to the derived category. So even if you start for a sheaf, from the point of view of complex, thinking of it as a complex only in degree 0, if you take its direct image, you get a complex which is non-zero in various degrees. And we'll see example of that. Okay, so in fact, the higher direct images are themselves sheaves, but separately they do not determine this object in the derived category. So might be the special case, if you want to go back to Tarski-Seidenberg, is what is motivating. Suppose you have let's think of F as a polynomial map from X to Y, and take the constant sheaf on X. So F is the constant sheaf on X. You look at its direct image functor, direct image to get a sheaf on Y. But what is this sheaf? So first of all, this is an object in the derived category. So you should think that the stalks of this are complexes. The stalks of RF star F should be complexes. And in fact, the stalk for every point in Y, the stalk of RF star F at Y is the complex which is the homology of the fiber of Y. So this direct image.
So what is your homology that you take all the way to the bottom there? What is it with?
Yeah, so this is the homology with the constant sheaf A.
Oh, okay.
So I should have said that it is F restricted to the fiber.
Yeah, okay. Oh, okay. It's a sheaf homology. Okay.
But it's the usual homology.
Yeah.
A is cubed. With coefficients, rational coefficients. Okay, so in fact, we can forget about the rest. I think this is the main thing to remember. So that's a consequence of something called the proper base change theorem in sheaves. Okay. So, and just to press this point a little bit, so let's. So we have talked about three different pictures of more or less the same thing. For quantifier elimination, which is something in logic, the fact that the image of a semi-algebraic set is semi-algebraic, which is something like in geometry, and then this sheaf. How does it work for the very well-known example of discriminant of a real quadrant? So the logical formulation in Tarski-Seidenberg is that, well, if you have this quantified formula with two free variables b and c, you can eliminate the quantifier and you get a quantifier-free formula, which is geometric formulation. Well, you have a real variety in the XBC space given by one equation. You have the projection, and well, the image of this projection is this set in blue. That's a closed set, that b square minus c is. But what is this sheaf theoretic formulation? Well, you have this sheaf, which is, you can think of it as a constant sheaf on R3 restricted to V. It's a proper way of writing it. And then you have this derived image of that sheaf from upstairs, downstairs. And what does that look like? Well, this looks like that if you look at the stalks, so if you have a point in the red part, then the stalk is 0. If you have if you are on the boundary, like I should have said, no, so if you are in the blue part, V, then the stalk is a complex, but it's concentrated at degree 0 because the fibers have no higher homologies, it's just 2 points. If you took something more complicated, then you will have higher homologies. So that's just Q plus Q. And if you are, though, on the boundary, like W, then the stalk is just 1 point. So that means that the direct image gives a finer partition if you at least think of the places where the stalk remains locally constant. Then the Tarski-Seidenberg, which just gave you a partition of the blue and the red. But now you have blue, red, and the black. So that brings us to the notion of a constructible sheaf. So this was, I guess, goes back to the definition of Kashiwara and Shapira in the book Sheaves and Manifolds, but goes back further to work of Kashiwara. And in fact, you can define these objects, of course, not necessarily on semi-algebraic sets or constructible with respect to semi-algebraic partitions, but might be more general category of O-minimal structures, but we will restrict ourselves to semi-algebraic sets. So if X is locally constant semi-algebraic set, object in this bounded derived category of sheaves of A modules on X. Then it is constructible if it satisfies two conditions, that there exists a semi-algebraic partition of X into locally closed semi-algebraic sets, such that these homologies of these complexes are locally constant. So these are sheaves, the AJ of F. So they are locally constant on the elements of this partition. And we'll call such a partition to be, so that's my terminology, it's not impression, but subordinate to F. So of course this is not anything canonical. So a partition of a partition, subordinate will also be subordinate. And such that the stalks are finitely generated. So for us this would mean that they're the homology of the stalks. So for us this would mean they're just finite dimensional Q vector spaces. And such that there exists an N such that the AJs are 0 for all J bigger than N. In absolute time. So we'll denote the category of these objects by D, B, S, A of X, and S, X, and so semi-algebra.
I'm a bit curious. Your F was already a bounded complex, and then does taking stocks in homology can make it unbounded?
So it
It doesn't.
right. So maybe I shouldn't have that B over there.
Ah, okay.
When you say local locally constant? Is that the same as saying that locally all the stocks are the same?
Well, what do you mean of the same? So this is a sheaf. To say a sheaf is locally constant means that there exists an open cover of C such that restricted to each cover is a constant sheaf. So that would imply something, as a consequence will imply that the stocks are isomorphic. No, no. Homology of the stocks.
Oh, I see what you mean. Okay,
What does the little SA stand for?
Semi-algebraic.
Ah.
Because we can, so might be that question is that we should be careful about things like this. So if you take this thing upstairs and you project it downstairs and you take a constant sheaf here and you look at the homology of the stock, so of course they are isomorphic at all places, but it's not locally
yeah,
constant.
yeah, thank you.
So, what the theorem of Kashiwara-Shapira is that these constructible sheaves have stability properties that mirror those of semi-algebraic sets. So, for example, if you have a semi-algebraic map, constructible sheaf on F and G, then the direct images and the inverse images, they are also constructible. In fact, they stable under all these 6 standard operations of Grothendieck. So I don't want to define this, certainly not this one. That one is respect to. Okay, so and also the inner home and the tensor. So that's the end of the qualitative part. We have to cover it too much time. So next part is what I would call quantitative, because all this was about stability under certain operations. So going back to semi-algebraic sets, so the Tarski's and effective versions of Tarski-Seidenberg, it's a pretty long history. So original, so Tarski's theorem was, of course, itself effective. So there's an algorithm, but it's kind of very bad complexity. But doubly exponential algorithm, following from something called cylindrical algebraic decomposition, was given by Collins simultaneously by Utrecht, who wrote a thesis, but I think it was not published, using cylindrical algebraic decomposition. So this, but the bad thing about this algorithm is that it is doubly exponential. Now, for the rest of the talk, whenever I take the projection for getting some variables, I would restrict myself to forgetting half the variables, just to keep the notation simple. It does not make any difference whether you forget. So Collins' algorithm would say that if you have a semi-algebraic set in Rn defined by S polynomials of degree at most d, look at its projection, then you can describe this projection in Rn over 2. So, but the number of polynomials and their degrees that enter into this description would be bounded by something like S d raised to 2 raised to some constant tensor. So when we say doubly exponential, that's the kind of exponential. But then we can do better. We can do singly exponential to reduce this constant to here. And there's a new ingredient which comes from Morse theoretic idea, so we call it the critical point method. And using it, Grigoriev and Vorobjov, more or less at the same time, or Jim Vanegar, proves that this complexity, and now I'm being a little bit fancy here, so I'm talking about these functors, pi n, so these f epsilon and f all that I introduced before, which goes from semi-algebraic sets of Rn to sets of Rn by 2 are bounded singly exponential, one level of exponent down. And later there are more improvements and more precise estimates, so some due to me and all I can go on, late 90s. I'm not going to talk about this in precise steps. But what I want to mention is this. So one would then like to ask what happens in the category of constructible sheaves. And of course one has to be careful. So what I would like to say is, just as before, that these two functors have complexity, algorithmic complexity, which is single exponential, then that I should say that the direct image functor from constructible sheaves Rn to Rn over 2 should also be bounded singly exponential. But to make this statement precise, I should, of course, have to define what do I mean by complexity of a constructible sheaf, and well, essentially that. And what do I mean by an algorithm? And of course, this is something new, so I'm not saying that this is the only way to define it, but what I thought was somewhat natural from the point of view of thinking about the underlying partition subordinate to constructible sheaves is the following. So suppose that if you have a constructible sheaf in Rn, for technical reasons we need that it has proper support, so that's why we consider in this theorem sheaves not over Rn but over spheres, but then proper support is automatic, but here we need to say something. But let's forget about this technicality. And such that there exists a semi-algebraic partition of Rn subordinate to F, and this semi-algebraic partition is defined by, let's say, S polynomials of degree at most D. So the sign conditions of these polynomials give you a partition of Rn into locally closed semi-algebraic sets on which is subordinate to this constructible sheaves. And then the first statement is that then there exists a semi-algebraic partition of Rn over 2, which is subordinate to the direct image, which depends just on this partition, whose complexity is Sd singly exponential. Meaning the exponent is a polynomial in M. And by complexity I mean, of a partition, I mean the number, a bound and the number of polynomials in their degrees. And moreover, there exists an algorithm to obtain this partition starting from the partition upstairs.